All right, welcome back to, this is the third video that I'm making so far on reverse engineering the Scuzzy CD audio player, which is written in BASIC. If you haven't seen the previous two videos and you care about the subject, then I recommend you go and watch those. I'd like to say first off that I'm trying to improve the quality of the audio for this video. I'm recording these videos on my phone and I had just been using the regular mic, but I have like a freezer in my basement that turns on and kind of interferes, and the quality of my voice was not particularly good. So anyway, now I'm using a condenser mic that's hanging off my lapel, a lapel mic, and I'm hoping that the quality of the audio is going to be better. So I've learned quite a few things that I didn't know last time. I was kind of just guessing at a lot of things the last time. And I made some good guesses, and I made some erroneous guesses. And so yeah, I just want to cover a few of those to start with. So here's our basic program. Now, one of the things that makes it kind of hard to figure out what's going on is that the program is partially written in German and it's partially in English. So most of the comments are in English. You can actually see from the comments here that there was some original code written by, I don't know, I think they're both German. There we go, .de on an email address. But the code was written by two people, and my feeling is that the first guy that wrote the code made the variable names all just be German sensible variable names. And the second guy came along and he modified the program, and his additions are more English oriented, but many of the original German variables are just kind of left as they were. So my guess is that, for example, this PU is probably stands for buffer. Anyway, so that is one complication. Now, I'll give you another example. So we have gone through the program. We went through pretty much the whole program within the last two videos. And I wrote down the line numbers of all the routines with, wow, that's very statically attracted to my screen. I wrote down line numbers with all of the descriptions of all the routines, those line numbers. And I wrote down all the variables that I could find. And I wrote down what I thought all the variables meant so that I could begin to make sense of what the program, how the program works. And by the end of the second video, I'd pretty much gone through the whole program and had a fairly good understanding about how it all works from top to bottom. There were some things that were not clear to me. And in the interim, besides just thinking about it a little bit more, I also went and I looked up a Scuzzy document, a PDF I found online that basically describes how the Scuzzy command set works with CD-ROMs. So now I actually know, I feel like I know more, but I still stand by what I did in the first place, which is to look at this sort of simplified, very practical example of how to use some subset of a much larger specification. I mean, if I had just looked at the specification, I wouldn't have a clue what subset of that specification would be necessary to get a CD player working on a Commodore 64. And clearly these guys have already done that. So it was easier to just kind of reverse engineer really exactly what their code does. But then wherever I had questions, now I have sort of a good framework, and I could go to the Scuzzy document and all of a sudden my questions, most of them, it all makes a lot more sense. So first place I will say that was confusing is we'll go to line 3500. Now these are 3 conversion routines, and they have these comments, MFS to LBN, LBN to MFS, and then this 100th of a minute to second. So the first thing to point out is that I was trying to figure out, well, what does MFS mean? And we have here this minute to second, and very clearly it's producing a minute and then a colon and then a second, and this routine is used to convert some playback location information that gets pulled from the CD-ROM while the track is playing. As the track is playing, it's constantly polling the CD-ROM, and as it gets a number, it's putting the number through this, and this is converting it into a minute and a second, and then that's returning, and then the program is spitting out where you are in the middle of the song in minutes and seconds. And so I thought, okay, well, the M and the S probably stand for minute and second, right? That would make sense. And but the F did not make sense. LBN, I correctly concluded, probably means logical block number. And I was also generally right that I had this sort of, I'd never read the spec before, but I had this dawning realization as I read the program that I understood sort of the concept where on an audio CD, or at least it's a little bit more complicated because you can have CDs that are a mix of data and audio, but let's just keep it simple and pretend that the CD doesn't have any data on it. It's just an audio, a CD-DA, digital audio disc. I was pretty much right that, let's say you have like an album of music, and the album is divided into tracks. Well, in reality, the album is recorded on the CD as this one long continuous PCM audio that's divided into a sequential range of blocks from beginning of the album all the way to the end of the album. But then you have this table of contents at the beginning, and the table of contents just tells you a number of... the table of contents is basically what defines the tracks by giving indexes for the start and perhaps the length of each track. So the audio itself is continuous, but the table of contents can be used to say, well, if you want to go to track 10, you look in the table of contents and it tells you what block track 10 starts at. And so if you simply skip to there, well, then it's as though the table of contents is kind of artificially segmenting what is otherwise a continuous chunk of data. So logical block numbers relates to that, right? Because the CD format, a block is effectively a CD sector. And typically for data, the sector would be 2048 bytes, which is a very round binary-like number. But in reality, a sector contains extra data, a little bit of extra kind of metadata about the sector to kind of validate the sector. But sort of, this is very, we're way out on a limb now, but sort of like how UDP packets don't require the same kind of back and forth confirmation. Like UDP packets are simpler than TCP packets. TCP packets have extra controls and extra information, and they require confirmation and so on. UDP packets are simpler. Well, digital audio is also simpler than regular computer data because it's just sort of streamed audio. So as a consequence of that, like if one sector in the middle of audio was somehow failed to meet the CRC validation, or, you know, like, so, okay, the data is corrupt. Okay, but that sector represents only 1/75th of a second of audio. And it's not going to corrupt your audio even if a sector has got a problem in it. So just like UDP is often used for streaming video, it's like, yeah, you know what? If there was a problem with a packet, it's like, who cares, because it's a streaming video and it's all in the past now, and you just have to keep going. It's a lot like that with music, right? So as a consequence of that, you don't really need to use those extra pieces of data in a sector to validate that the sector's data component is perfect. And so therefore, in order to use more of the raw capacity of a CD, each sector actually contains audio data that's more than 2048 bytes, because the audio data actually subsumes that extra little bit. So one block, which is exactly 1/75th of a second of audio, is 2,352 bytes. Well, that's actually just a sector on the CD, or a block, a logical block number. Now, here's what was confusing to me. This is a typo. I was thinking, okay, well, M and S must be for minutes and seconds, but what does that F mean? And I thought, well, like full colon was the only thing I could come up with. It was a harebrained idea, but you know, here's this full colon, right? I couldn't figure out, well, what would come between the M and the S? This is a typo. It's supposed to be MSF, which stands for minutes, seconds, and frames. And a frame is 1/75th of a second. So basically what you have is a second is 75 frames. And a minute is 75 times 60. And if we go to our calculator and we type in 75 times 60, we get 4,500. So these 4,500s that we're seeing here, that's because it takes 4,500 blocks to make 1 minute. And it takes 75 blocks to make 1 second. And then anything left over that's less than 75 blocks, like 50 blocks left over, that's a fraction of a second, but it's simply counted as frames. So MSF, minutes, seconds, and then leftover frames that all together add to less than a second. So that helps a lot, given that, you know, now we understand. Yeah, there's two things about the program, right? German variable names and then weird little typos like MFS to MSF. Now, the other thing that I found a little bit confusing, a little bit kind of, I don't know, annoying maybe about these routines is that in my mind, in my world, if you have two routines that convert between two formats, so here we have let's just call this MSF to LBN, but the very next one is LBN to MSF. That is a lot like, there are many other examples of this. So for example, degrees to radians, or radians to degrees, right? A pair of converting routines. Or maybe Petsky to ASCII, but then you have ASCII to Petsky. Another example might be, say, Fahrenheit to Celsius, Celsius to Fahrenheit. Okay, sort of a pair, these pairs of routines that convert back and forth between two things. So in my mind, whatever you feed in to one routine and you get out of that routine, you should be able to feed the out of that routine into the second routine, and the out from the second routine should be exactly equal, or as damn close to equal as is possible, depending on rounding and precision. The out you get from the second routine should be precisely identical to that which you put into the first routine, right? So for example, if you have, here's our complete interspace anthology, and we have our Petsky to ASCII. This is our Petsky table. So in ASCII, the uppercase alphabet is in this block. But in Petsky, the uppercase alphabetic letters are in this block. So if you were to put in a 41 for a capital A in ASCII, and you wanted to convert that to Petsky, it would give you back a C1. But if you took a C1 and you put it into the Petsky to ASCII conversion routine, the partnered routine, it should give you a 41, right? So the two should work like that. Now let's look at these. They just don't work like that. First of all, when you call MSF to LBN, its input is a track number. And then it's reading the bytes from the table of contents. And it's reading them out. It's reading the bytes out of the table of contents for the track. And then it's multiplying the minutes times 4,500. It's multiplying the seconds times 75. And then it's doing some wacky subtract 150. I don't know why it's doing that, to give you a number, which is a block number. Okay? But when you convert LBN to MFS, first it adds 150. Again, I'm not entirely sure why it does that. But then it takes the block number, it divides it by 4,500 to give you minutes, which it sets to this MM variable. And then it divides by 75 to get you this SS variable. And then it takes the block number and it converts it back into minutes, seconds, and frames. But this one comes from the table of contents, and this one goes back into variables. They're not symmetrical. So if I were to write functions like this, I would say, write a routine that extracts MFS from a track. Okay? You supply a track, it gives you an M, an S, and an F, preferably, not DD, but it should give you an F. So maybe MM, SS, and maybe FF instead of DD. And then, when you call MFS to LBN, it should use M, F, M, S, and F, give you BN. You call LBN to MFS, it should take the BN, convert it into M, S, and F. That's just my personal opinion. Okay. All right. Here's the next interesting thing that I learned. It's in the table of contents. So let us go to the table of contents routine. That's 2400. 2400. Okay. So here's the command, and we'll come back to look at what the Scuzzy commands look like and how the Scuzzy commands work, because they're pretty cool and I've learned something about them. So we compose the Scuzzy command here, and then we call 4000 to run it and have the data get put into the hard drive's RAM, and that is at 3600 in the 3600 hex inside the hard drive's RAM. Okay. Next, this basically blindly loads up to 512 bytes. So PE is a memory buffer in the computer that's 512 bytes, and we do a memory read for the maximum, which is the 0, which is 256 bytes. We loop from 0 to 255, read the data into the PE buffer, and then it immediately loops one more time, and it calls the high byte plus one extra page so that it grabs the next page, and it reads exactly 512 bytes. Well, that's not exactly how it works, because we can see that immediately after we've fetched everything into the buffer, 0 and 1, they represent the amount, the number of tracks there are. But they're not exactly the number of tracks. They are the length of data of the table of contents. That is what it says here. So rather than blindly reading 512 bytes, I maybe wouldn't do that. I would probably read 2 bytes first, and then once I'd read 2 bytes, and I know exactly how much data there is, you could then proceed to read precisely how much data there is. I think that would be a little bit faster. So the next thing to know, so basically the table of contents consists of 2 bytes that tell you how much data is in the table of contents following those 2 bytes. So that those 2 bytes aren't included in the amount of data that will follow, right? The next 2 bytes after that are numbers that tell you what's the first track and what's the last track. I find that a little bit weird. It's some technical thing. Like, you would think, well, isn't the first track always going to be like 1 or 0 or whatever it's called? But it seems that it's possible that the first track is not 1. So be that as it may. So next, what we do is it loads in. So it says 8 bytes per title. That's exactly what it is. It's 8 bytes per title. Now, I read some spec that said there are these null bytes. So you have like null, and then you have minutes, and then seconds, and then frames. But I think that there's either 2 ways to... I think that there are 2 ways to get a table of contents. And I think we'll look a little later to see how does it figure out. We'll have to figure out here which of these 2 modes it is. But the other mode could be that it's the logical block number in the table of contents. And I saw a description somewhere that said, first there's a 0 byte, a null byte, and then you have the high byte, and then the medium byte, and then the low byte. And then you have another null byte, and then you have a high byte and a medium byte and a low byte. And it's like, okay, we figured out in the last video that the reason, so these look like 24-bit numbers for logical blocks. And it has to be at least 24-bit because if you had only a 16-bit number, 65,536 1/75 of a second is only like 14 minutes. So you need a number that's bigger than 16-bit to represent the number of sectors that can fill a CD. Okay, but the revelation that I had is that it's not that the first byte is just some sort of a zero padding byte, and then you have a high byte and a medium byte and a low byte. It's a 32-bit int. The table of contents just has two 32-bit ints, and they're in big endian format. Now, why 32-bit? Because it's easier for computers to read in 32-bit chunks than it is to read in 24-bit chunks. It's just easier. You can just make a 32-bit word, really, and you just have this table of 32-bit words. Now, the first byte is the high byte, so it's 0. Well, yeah, it's 0, but it's not like it's a 0 padding byte. It's just the 0 byte of the 32-bit int, and it's the most significant byte, and it's 0 because CDs aren't big enough for the first byte to ever reach 1. It's a little harder to see that when you're on an 8-bit machine because, you deal with each byte at a time, right? So you load in the first byte and it's, oh, this one's always 0. Who knows? It's just padding. And then the next one, okay, that's a high, and and you track each byte one at a time. You have to multiply the, anyway. Okay, so that's for table of contents. Okay, the next thing I wanted to talk about is the format of these Scuzzy commands. Just like in here's the manual for the CMD hard drive, and just like when you write a command to the CMD hard drive's command channel, you open the channel, and the very first thing that you send is some kind of a command byte, right? So like even the Scuzzy command, what the first 3 bytes make up the command, S-C. But then following the S-C, you got a bunch of just like binary bytes, right? Values that could be anything. And that's the same for all the other kinds of commands, right? So for example, here's the command to position a file pointer inside an open record. It's like, okay, the first byte is a P. So P is the position command, right? And then after that, you get all these other bytes. Well, Scuzzy actually works a lot like that. But instead of it being sort of textual, it's just a byte as far as I can tell. I'm not sure about how those bytes were assigned. I'm just looking at this chart here. So 71 so basically in the Scuzzy command, the 71, that's the command byte, okay? So in the actual Scuzzy command list, if you look up a list of Scuzzy commands, I've got another computer here, so I'm going to look up Scuzzy commands. Okay. So here's a list of Scuzzy commands. And let's say 71. Now these commands are all listed in hex. So let's switch over here to hex and decimal and so on. So 71 in decimal is 47 in hex. And if we look up 47 in the list of Scuzzy commands, it says play audio MSF. It's like, play, that's a typo. MFS should be MSF. So literally 71 is the Scuzzy command to play. It's only a valid command. It's only a valid Scuzzy command for CD-ROMs, specifically for audio CDs. And it literally means start playing the audio starting at an M, F, and an M, S, and F signature. So the point is that the Scuzzy command set itself contains a suite of media-related playback commands, right? So it's very basic. What was the so to read in the table of contents, for example? So the point is now that now that we know what these Scuzzy commands are, we can actually we can look up how the command is structured in the documentation. So 2400 was the table of contents. So we'll go into 2400. Okay. So here's the command 67. That's in decimal. So we'll put 67 in decimal. That's 43 in hex. 43 in hex is the command that says read table of contents, read TOC, exactly as it says here, read TOC, PMA or ATIP. I'm not entirely sure what PMA or ATIP are. And so we're going to go in the documentation to read TOC. So read TOC command is page 51. So we're going to pop down here to page 51. Okay. Okay. So here, whoops, don't get that monitor too close. Page 50, so this is the command. So you have bytes, hoping you can see this. You have bytes, you have bits. So the operation code is 43 in hex, that's 67. Next, we have reserved, MSF, reserved format. So these are bytes. So the second byte, or the first byte 1 instead of byte 0, I don't know what that logical unit times 32, I don't know what it's doing in there because these say reserved. But I do know that there's an MSF bit, which is right here. It's bit 1, which is equal to 2 in binary. And so the fact that they're adding +2 on here is going to set this MSF bit. Okay? The next byte is a 0, and that's a 0 for format. So format must be 0, right? Format field is defined in table 68. So here's 68. So we've got 0 is table of contents. 1, session info. 2, full table of contents. including extra data. 3, some other more detailed forms of tables of contents. But 0 is the track and sector number field specifies starting track number for which the data will be returned. For multi-session disks, this command will return the table of content data for all sessions and for track numbers. AA only lead out. Yeah, so it gets technical, right? It's just automatically technical. But the point is that that 0 is a format byte. Then we have reserved, 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 in which we have 0, 0, 0. Then we have track/session number in hex. It's another 0. Then we have allocation length. Allocation length. And lastly, we have control. Control is 0. Allocation length is BL, and our BL is a variable that we've defined as 1 block. Okay? So this basically is the command to read table of contents as in the format MSF. Okay. Next, what we need to do is say we need to figure out what does the table of contents actually look like. So here's what a table of contents actually looks like. First 2 bytes, again, most significant byte coming first, is the data length. Second 2 bytes, first track and last track. Here are our, here we pull them out. So TN, track number, data length. Okay, response format. Response, data format for type 0000. The data consists of a 4-byte header and 0 or more track descriptors. The response data is dependent upon the format specified in the format field. So we have our table of content data length. Then we have our first track and our last track. And then following that, we have 8 bytes. We have 8 bytes of table of content. So 0 is reserved. 1 is divided between ADR. The upper nibble is ADR. The lower nibble is control. 2 is the track number. 3 is reserved. So I don't think that we're doing anything with ADR or control, and I don't think that we're really caring about track number. But 4 to 7 is the logical block address. Four to 7 is the logical block address. And you can see that most significant byte first, that's why that is 0, just as I mentioned earlier. It's going to be 0 because there aren't 32-bit large numbered logical block addresses. Now, here's the thing that I'm confused about at this very moment. Because of this 2, it seems as though we're requesting the table of contents to be in minute, second, frame. This here is, saying logical block address, most significant byte. Type 1, type 2, let's just figure out whether this +2 is actually what I think it is. So, if we list 7,000, logical unit is 0. Indeed. Okay. So 0 times 32 plus 2 is definitely going to be 2. So coming back here, the request that we make is this request here. So we have our operation code 67. Then we have the most significant, the MSF bit is set in the second one. The third defines the format, and it's 0. So it seems to me, therefore, that we are getting format 0. But we've requested it with the MSF bit set. So it's going to be, it's in this format, but this final section here, so it's 8 and 8 and 8 and 8 and 8 and 8 and 8. But this last thing here, instead of being just a 32-bit int for logical block address, we've specifically requested it as MSF instead. I'm gonna run out of battery life on that laptop. So now, let's go to all the way down to 60,000. So this is the main program where we're going to, so we spit out the table of contents here, read a table of contents, we spit out the sort of main menu thing, and then we have these options. A for all tracks, this guy for exit, R for random, P for play the whole disk and exit, and then next we have these track guys, right, where you've specified a specific track. So if your track is within the track specified by first and last track, then we're going to go to 3500, which converts MFS to LBN, but that's not quite right. What 3500 does is extracts the MFS, the MSF, pardon me, the MSF for the specified track, and then converts it into a logical block number. Now, why does it convert it into a logical block number? Because this format, here's why. This format in the table of contents has not a start and end address. It has whatever the heck this crap is. And then it has a start address. Is that right? The table of contents data length indicates the length in bytes of the following table of contents data. The table of contents data length value does not include the table of contents data length, its field itself. This value is modified blah 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 blah. The first track indicates the first track number, the second track, last track. The ADR field gives the type of information in the subchannel. The control field indicates the attributes of the track. A track number field indicates the track number, blah, blah, blah. The logical block address. Okay, so the logical block address contains the address of the first block with user information for that track number as read from the table of contents. Okay, so this logical block address is the logical block address of the first block containing the information for that track. Okay? An MFS bit of 1 indicates that the logical block address field contains an MSF address. So by setting the MSF bit, we have requested not the logical block address of the first block, but the MSF of the first block of the track. So, what do? The very first thing we do is we convert the MSF for that track from the table of contents into a logical block number. Why not just request the table of contents with a logical block number data in the table of contents? I'm not sure, but maybe we'll see shortly. Now, assuming the first track is at index 0, and we hit track 1. It's going to look up index 1, which is actually looking up the start block, which start MSF, which it converts to blocks. So we're looking up the first block of the track after the one that we want to start playing. Then we -1, maybe because -1 means that's the last block of the track we do want to play. Then it does a go sub 3540, which converts the last block of the track we do want to play into an MSF address, which is stored in the variables MS, MMSS, DD. Okay? So now what we have is a table of contents entry. Well, we technically have, we have a table of contents entry that's in MSF, and we also have numbers, variables, M, M, S, S, and D, D that hold the MSF of the end of the track. Next, we set NR, which might be German, I have no idea, to be T-1. That's the actual track that we want to play. That's the index. So if we've said we want to listen to track 1, NR is going to be 0, so that'll be the index into the table of contents. Next we do a go sub to 2700, which is play MFS. So let's pop over to 2700. Super, super simple. And we can immediately see here that the Scuzzy command is 71 in decimal. So 71 decimal in hex is 47. We can now, low battery. Yeah, hold on a second here. Maybe I can plug this in somehow. Yeah, well, we'll get there. We'll get there shortly. I'll plug this in a second. I got 10% battery life left. So let us come up here to, so play MSF command, page 30. Come down here to page 30. So page 30, MSF command, here it is, operation code 47 in hex, that's what it is. Reserved and reserved, again, no idea why we're sending this logical unit times 32, but it's going to be 0 because our logical unit is 0 anyway. Reserved and reserved, reserved, reserved. Then what do we have? A start MSF, an end MSF, and then we have a control byte, and the control byte's 0. Okay, let me plug in this laptop. So maybe we know now why the table of contents. Maybe we know now why the table of contents was read in MSF. Because the table of contents does not tell us how long a track is. So we say, okay, where's the start of the next track? Convert that to a block, subtract one block from it, convert that block back to MSF. Now we can look up the start MSF from the table of contents, and we've computed the end MSF, and lo and behold, the start MSF is from the table of contents, from the table of contents, from the table of contents for NR, which is the index of the actual track in the table of contents, and the end is the MM, SS, and DD. All right, I mean, it actually works. It actually works. It works. Now, there were a couple of things in here that I don't think were even used. So PU gets defined as 9 at the very beginning. And DP gets defined. I thought it stood for data pointer. Then I thought maybe it stood for data puffer, dot and puffer for data buffer. But I'm not sure if so DP and PU, I'm not sure if they're ever used. And then later we'll come back to read subchannel. We'll see exactly what that does. Oops. So PU, which might be buffer, 9. Inquiry command. Test unit ready command. Read the table of contents. PU is not used in reading the table of contents. Play MFS, as we just saw. PU is not used. Reading the sub channel. We're going to come back to this in more detail shortly. But I don't think PU is used anywhere in here. No, I remember we went through this at length last video. Starting and stopping the unit. Again, 27, it's just another Scuzzy command. Again, PU is not used. We have our conversion routines. PU is not used. We have sending our actual Scuzzy command. The request sense doesn't get used for anything. The actual command being sent to the CMD hard drive. PU is not used. Scanning the bus for the CMD hard drive. I didn't really look into this routine in much depth, but it doesn't look like PU is used there. Scanning the Scuzzy bus. Okay, DP is defined here. Again, it's defined again, second time, for some reason. But it certainly doesn't look like PU is used anywhere in there. In fact, it doesn't even look like DP is used in there. So I don't know why DP is even defined. It's never used in there. Or is it? Am I missing it somewhere? I don't think so. I don't think so. Okay. So now we have, what did we call 6000? Clearing the screen, drawing the main screen. It's definitely not used there. The action screen, which displays the status message, definitely not used there. So init screen, again, this defines some weird variable, PU equals PU0. Okay, nothing's been loaded into PU. I don't know. Okay. Scanning. This is the thing that kicks off the process of scanning the bus. Just these two routines call routines we just looked at to scan the bus, but that gets shortcutted by this self-mod line. And then we have some text, so that's not going to be anything to do with PU. And then we have that stuff that overwrites. This is the self-mod keyboard buffer stuff. Then we have our input substitution. So this is sort of our advanced keyboard input. Advanced for basic. Obviously in C64 OS this is all going to be proper toolkit, mousy clicky stuff. Then we have the main program. Which basically consists of menus, calling routines we've already seen, doing the play all and the randomization, PE, but not PU, playing the entire CD, doing random, and we're done. I mean, the point is PU and PU dim, they never get used. They never get used. I mean, unless I missed them in there, they never get used. And I just find that kind of annoying because, what's the point? Why do why do you leave that cruft in there? I don't know. All right. Next, let's return to subchannel. So, subchannel is basically a loop. We wrote that down, right? Read subchannel is a loop that checks for time remaining, polls for stop or track changing input. And it just keeps looping and checking for remaining time and printing that out until the track is done, and it also polls for user input along the way. So let's go check that out temporarily, for a moment rather. So the main thing that it does is it defines this 66 Scuzzy command. So 66 is 42. Maybe we can pull this laptop back down now that we've plugged it in for a minute. So we're going to go back up to the table of contents. This is basically reading a subchannel. Reading subchannel. Okay, reading subchannel is going to be page 45. Pop on down to 45. So here we are on page 45. So reading a subchannel. There's our 42. Byte 42 is operation code 42. Here, it's the same sort of format as the table of contents, reserved and reserved, so I have no idea why we're taking that logical unit, multiplying it by 32, because it's reserved, but unless this documentation is out of date. Plus 2, it's going to set the MSF bit, so we'll pay attention to that. Next, we have this sub Q, that's bit 6. We're passing in 64, that's bit 6. So we are requesting sub Q. Next, subchannel parameter list is 1. Okay, not sure what that's going to do. Subchannel parameter list codes. 1 is the CD's current position. Okay, so we're asking for the CD's current position. What do we got next? 0, 0, 0, 0, 4 zeros in a row. 0, 0, 0, 0 for high byte. Low byte, 15, and then a control byte of 0. So track number hex of 0. Track number field specifies the track number from the ISRC data is read. This field may contain a 0 when the format code is not. Three. So I think that that's simply allowed to be a 0. It's basically telling us it's allowed to be a 0. Allocation length. So sub Q bit is we're setting the sub Q bit. The sub Q bit set to 1 requests that the target return the Q subchannel data. The sub Q bit set to 0 requests that no subchannel data be returned. This shall not be considered an error. It looks to me like you basically just always have to set that high. So set it high and you'll get the data. Okay, and again, we already looked that subchannel parameter list being 0 is going to give us the current CD position. And so all and then the allocation size, 15. So the only thing we really care about is the response data. Let's plug the laptop back in. And we're just going to check out, what do we pull as a response from this command. So we send the command with 4000. And assuming there's no error, we read from our memory buffer 15. So we've said in the Scuzzy command that we want to allocate 15, and then from our memory buffer in the CMD hard drive we pull 15 characters. Then we loop over all the 14 characters, and we copy them from the CMD hard drive's memory buffer into the computer's buffer, which is PE. PE is just like, we talked about this last video, PE is just a generic buffer in the computer, which is a copy of the data that has been dumped from the Scuzzy command into the hard drive's buffer. Okay, so MR, reads it in. So we read all 15 bytes, and then the only ones that we use are 13, 14, and 15. Okay? So what we're looking for up here, is to say we have specifically requested the current position of playback. And so here we are, subchannel data format for 01 CD current position. Table 59 defines the response data format. So we're using bytes 13, 14, and 15, which interestingly enough don't appear to be here. What the hell? What the double HE hockey sticks? The HE double hockey sticks. What is going on here? What is going on here? What is going on here? I don't know why this is in 13, 14, and 15. Like, this is clearly minutes, seconds, and frames. And this is also a bug that I pointed out last time, but because it's so low precision, it literally doesn't matter. I don't know why it's in 13, 14, and 15 and not. It should be in 9, 10, and 11. Track relative CD address. I don't know. It doesn't make any sense to me. I don't know. Ah, I know. I understand. Because the sub-Q channel data has a 4-byte header. So you have 4-byte header, and then you have the subchannel data following the header. So you'll have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16? That's the reason. That's the reason. All right. Cool. Cool. Super cool. And now we are 1 hour into this video, and I would say now we have, over the course of these 3 videos, we have a complete understanding of how this program works. There's basically nothing about it now that I don't understand. So where do we go from here? Or do we call this video a wrap? We call this video a wrap and we say, now we understand. Maybe we'll just summarize. Maybe I'll summarize, because what are we at here? I'm at 1 hour and 10 minutes. Last video was 2 hours and 10 minutes. So now that we fully and completely understand how this program works, let me summarize it for you. From the top. Huh, interesting, that works, eh? List dash, cool. So from the top, we clear the screen, we set it into lowercase character mode. BD is the boot device, which only actually gets used if we're going to be self-modding this program. Then we declare these variables, PU, which never gets used, TD, which is the track data, with support for 36 tracks. The 7 we discovered recently that dimensions, the number that's specified in a dimension is actually the size of the dimension plus 1, because it's like Microsoft expected it to be expected you to think of it as 1 based. So if you say 7, it's like you can go from 1 to 7. But at the same time, you can also put in 0. So if you think of it as 0 based, it's 0 to 6 plus 1, because you can also use 7. But if you think of it as 1 based, it's 1 to 7 plus 1 more, because you can also use 0, right? Okay. So this is technically enough for 37 tracks, 8 bytes per track. And then we have this memory buffer of 512 bytes, which is just a memory buffer that you can use to read data out of the CMD hard drive's buffer. We have a block length, which helps us with later calculations. Session number. I believe session number is never used in this program. It's another example of PU9. It is never used. MH and ML are used. These represent hexadecimal number 3000, which is the address of an 8 kilobyte block of free memory inside the CMD hard drive. DP, this is 3000, but I don't think DP is ever used. Z and L are used simply for the user interface. You can quickly print out long one across the screen of dashes or one across the screen of blank. Next, what we'll do is we go to line 60,000. We just go to 60,000. Okay, so let's go there. Now, in 60,000, first thing we're going to do is scan for the hard drive and the CD-ROM. So we'll go to 7,000. Now, the program is self-modding. So if it has been self-modded, the device of the CMD hard drive is already written. The ID of the CD-ROM is already written. The logical unit of the CD is already written, and it returns. Otherwise, if this line is not there, it will go sub 5000 to scan the CMD bus. It will then, assuming that it finds a CMD hard drive, it will go to 5200 to scan that hard drive, the very first hard drive. We discussed this last time. If you have 2 CMD hard drives, it only detects the first one. So if you have 2 CMD hard drives, unlikely, but if you did, and the CD-ROM was hooked up to the second one, this would not work. 5200 will scan the Scuzzy bus for all device IDs and all logical unit numbers of each ID, looking for something of type 5, which is a CD-ROM. And then it spits out this stuff to allow you to self-mod the program with this line. Let us now return to 60,000, which is where we left off. So 7,000, it's going to set device for the CMD hard drive, ID for the Scuzzy ID, LUN for the logical, or LU rather, for the logical device number. It immediately prints out a message telling you to insert a CD, and then it goes to 2040. 2040 is the command to test the unit. Now, I haven't looked up testing the unit in the Scuzzy manual yet, but I believe it tests to make sure that the unit is connected or online or something. So let's go back to 60,000. Okay. So it tests the unit, just as the comment says. Next, goes to 6100. Which spits out a status line, or it replaces the line So that's going to replace the line that says, please insert a CD with the word status or something else. Okay. So if the device is not ready, it will continue to probe it by continuing to go to 2040, just over and over and over again. It'll keep trying to go to 2040 until eventually the device is ready. Then it will say that it's reading the table of contents, and it will read the table of contents. Now we've reviewed reading the table of contents, but we'll review it quickly again. So it's going to send the table of contents command, read the table of contents. 2 means bit 0, bit 1. This 2 means that we want to get the table of contents with the format being in minutes, seconds, and frames, not logical block addresses. And we've said how much space we have. That's a bit weird to me. It looks like it's only one sector, so I'm not exactly sure why. So we're sending in 2,352 into here. Honestly, not sure exactly what would happen if you made that smaller, but who cares? Then we memory read all 512 bytes. We memory read a full 512 bytes from the hard drive into our memory buffer. Now, 512 bytes would be enough for, we can support 37 tracks, 36 tracks actually, 37 technically, but the program thinks only 36. So let's say 36 times 8 bytes per track. Sorry, let's do that in decimal. 36 times 8 plus 4. Okay, 292. Why we're reading in a full 512, I'll never understand, especially in slow basic. However, we'll at least get everything. TN, I don't know what TN, I mean, TN is telling us how much, TN should be telling us how much data is in the track, the table of contents. But honestly, I don't think TN's ever used again because nobody cares how much data is in the table of contents. FK and LK are used as the first track and the last track. I think 99% of the time they're going to be 1 and however many tracks there are. But this at least helps us to know in the user interface which tracks we're allowed to pick, which ones are valid, and then it will look those tracks up in the table of contents. Now, even if it says that it's track 1 to track 12, we put the first track's data into index 0. Okay? Read, start, and end times. So here we read 8 bytes at a time, and we stick them into the track. So we now stick, for each track, we stick into track data at the track, 8 bytes. Table of contents. Now, honestly, we don't use anything except the last 3 for minutes, seconds, and frames. So really, we don't really need to record all that data. We could just skip some and okay, but that's what we're doing. So now let us return to 60,000. Okay, so we've read in the table of contents, and as soon as we're done reading in the table of contents, we say please choose, and we print that out on the screen, and we print out this this little menu here. So now we have all, quit the program, random, play the whole disk and exit, or play a specific track. So let us suppose that we're going to say all. So let's jump to 60,500. Okay. So what do? We make a loop that goes from the first track to the last track, but bear in mind that's not zero based. So T is going to be 1 to say 12, not 0 to 11, but our index of tracks is 0 to 11. Okay? So we will now go sub, the very first thing that we'll do is go sub 3500. That is going to, we just looked that up earlier. That's the MSF to LBN. So that is going to, so T, first track, T is going to be 1. So it's looking up in the table of contents 1, but that's not the first track. That's not the first track. That's the track after the one we want to read. So it gets the logical block number for the end of the title. It actually gets the logical block number for the start of the track after the one that we're on. We subtract 1, so that now we're on that's the last block of the track that we want. Then we call 3540 to change this block number back into the variables SS, DD, which is actually MSF. Then what we do is we say that NR is going to be equal to track -1 because we're counting from 0, just as the REM says. Now, why we need NR and we can't just plug in T-1 in the routine up above, I don't know, but who cares? Next, we do jump to 2700. 2700 is play MSF. That's going to issue a command. We'll jump there. We'll go back to 60,500 in a second. So we'll jump to 2700. This is the command to play music from a start MSF address to an end NSF address. We look up the current track we're trying to, for the start address, we look up from the table of contents the current track we're trying to play, 0 based. We look up its 5, 6, and 7 bytes. Those are the last 3 bytes of the 8-byte range, which we found in the table of contents is going to be M, S, and F, so that's the start address. Our 3540 line, which converted the logical block number for the final block of this song into MMFFSS, MMSSFF, become the last play. We submit that to the disk and it starts playing. We go back to 60,500 and now we're going to print that it's playing all on the screen. Now we're going to go sub 2,800, and that is the read subchannel. So we go to 2,800, and we print out a little bit of modified user interface. Okay, so what does this do? This is all of a sudden something that I hadn't fully figured out. But we know what we're looking at now, don't we? So NR is the 0-based current track that we're on. 5, 6, and 7 are the M, the minutes, seconds, and frames. And we're going to multiply that by, so the minutes multiplied by 4,500, because that's how many sectors are in a minute, plus the number of seconds times 75, that's the number of frames in a second, plus however many frames there are in the second. Okay, so PA is going to be the number of blocks. In fact, we can write this down. PA is the start of track logical block number. That's exactly what that is. You see, now I actually know what that is. Okay. PE is, so MM, SS, and DD are the equivalent of the table of contents 5, 6, and 7, but the table of contents 5, 6, and 7 is the start of the song. MM, SS, and DD are the end of the song. We multiply that by 4,500. We multiply that by SS. You know, we already had it. We already had this in BN minus 1, right? So PE, we now know what PE is. It's the end of the track logical block number. Okay? We know what that is. So PG is the end minus the start. Again, this is in logical block numbers. So PG is the total number of logical blocks. Okay. Yeah, so PG is the total number of logical blocks divided by 4,500 is going to be how many minutes there are. Is that what I said PG is? It's the total play time. It's the total play time in minutes as a float. Yeah, that does make interesting sense, doesn't it? Yeah, as a float. It's the total play time as a float. Minutes as a float. Yes. 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 That's what that is. Now we know what 3600 does. So let's go examine 3600. So now we know 1/100ths of a minute. Yep, because it's a float. So B is the integer value of A. B is the minutes. And so so we go the stir value of B, and then we say write to. Honestly, I don't think that it can exceed 2 digits. So I'm not entirely sure why it bothers to write. So write to gets only the rightmost 2 digits. Yeah, so we've inted A. So we've basically, B is just the minute component. So then we go A minus B. That's going to give us only the fractional component. The fractional component times 60 divided by 100. C gives us, well, let's say it was 2 point, sorry, let's say it was, we gotta go to complex mode. Let's say it was 2.35 minutes. So we need to figure out, well, what is 0.35 in seconds? So B is the int of this. That's going to be 2 minutes. And then we go A minus B will be 0.35. So we'll go 0.35 times 60 is 21 divided by 100 is 0.21. That is 21 seconds? Is that what that is? But then we immediately multiply it by 100. What is the point of that? Why divide by 100 only to multiply by 100 a half second later? Why do that? Why do that? Why do that? I am not sure. Not sure. But ultimately, this just converts the fractional component into seconds. And so then it takes the string value of B as a minute, colon, and then it does some padding, I guess. Right. Yeah. So that's kind of cool, actually. I like how it does this as well. It takes the string value of C, and then it does the mid 2 for the string value of C. I don't know why it does a mid, but then it prepends it with a 0 just in case it's only 1 long. So if it was 1, you'll get a 0, 1, and then we grab the right 2, so we grab both 0 and 1. But if it was already like 15, well then we get a 0, 1, 5, but we only grab the right 2, so the 0 gets lopped off again. So that's kind of a tight way to do that. I like that. Yeah. Okay, so let's go back to, we're still in the middle of 2800, reading the subchannel. Okay. So we got the length of the song by taking the difference between. So the trick is that the table of contents is MSF is the minutes, seconds, and frames start offset in the large entire continuous thing, right? So let's say an album is an hour long, and it's like, okay, it's an hour long. But track 10, therefore, is going to be, oh, well, that's minute 45, second 31, plus some fraction of a second. That's the start of track 10 in the entire continuous 1 hour album. So we convert that time into a logical block number. Then we know the minutes, second, and frame of the end of the song, again, inside the entire massive 1 hour long length of PCM data. And we convert that into a logical block number to figure, okay, well, what's the logical block number that represents the end of the song? And so now we have two logical block addresses, and we can subtract them to get a number of logical blocks that this song is made up of. And then we simply divide that by 4,500 to get how many minutes it is as a fraction. Then we use 3,600 to convert that decimal hours float into minutes and seconds. Minutes, rather. Floating minutes, fractional, into minutes and seconds. And next, what we do is we do this read the subchannel. This too says we want to get the subchannel data in MSF. This says give us the data, it's basically required, and everything else doesn't matter except that it's going to be 15 bytes long. Okay? And so that gets read, so that sub-channel data gets read into the CMD hard drive's memory. And then we use this MR command rather, to read from the buffer address, that's 3000 in hex from the CMD hard drive's memory. We read 15 bytes. We read that using the error channel into our standard in-computer memory buffer. Okay. Wow, no, I went too far. That's right. Into our computer's memory buffer. So now what we're going to do is, now from the memory buffer, we have already concluded that there's a 4-byte header, and then there's a 12-byte subchannel data, and the final 3 bytes, so that's 13, 14, and 15. Although this should be 0 to 15, not 0 to 14, so that's a little bug. But who cares, because it's only for the least significant frame number. Tiny fraction of a second, so we really don't care. I have no idea why it's adding on 0.004. Not the slightest clue why it's doing that. Not that it even matters in my opinion, but we'll see. So this is going to convert the MFS into a play position. So P is play position, but it's play position in as a logical block number. Okay. And its play position as a logical block number. Not quite. Not quite. Not quite. Just from this parenthesis to this parenthesis does it convert it into a logical block number. But then it divides the number of blocks. This MSF is relative to the start of the track. It's relative to the start, not of the track. It's relative to the start of the play MSF command that was issued. So it, just from this parameter to this parameter, is converted into a logical block number relative to the range of blocks that we're playing. So if we say, okay, we're going to start playing at block 1000, and then it starts and it plays 100 blocks, then the response to this is going to be block 100. It's not going to be 1100, it'll be just 100. So then we divide that by 4500 to get minutes as a fraction. Minutes as a decimal, as a floating decimal. And then we do exactly the same thing here to convert it into minutes and seconds minutes colon seconds. That's the current play position. And then what we do is we take PG, which PG was the total number of blocks in this play range minus, there's something that doesn't make sense here, but I'll get there in a second, minus PP, which is the current position, to give us the time remaining. Except that this current play position block is divided by 4500. This one is not divided by 4400. And so that doesn't really look right to me. I don't know how that works. Where was PG defined? PG is defined right here. Oh, yeah, right. PG is pre-divided by 45,000. Oh boy. Oh boy. Yeah. Right. And PP is also divided by 45,000. So PP is minutes as a fraction, and PG is length as minutes as a fraction. So I actually made a mistake in what it is that I recorded on this piece of paper. Yeah. So technically, PP is current play position as minutes float, and total playtime is also minutes as a float. Gotcha. Yeah, that's exactly what it is. So PP gets this block length and then divides it by 4500 to get minutes as a float. Then it spits out minutes as a float. Then it takes PG, which was the length of the song, and minutes as a float, and does the difference between them to get a difference between the minutes and as a float of the total length of the track versus how far you are in to get the difference between them. And then it converts that to minutes and seconds. Next, it polls the keyboard to see whether you've pushed one of these keys, and if you haven't, it just keeps playing the track and keeps sending the same Scuzzy command and running all these numbers on it just to update the time. And if you push plus, it will simply return, fall through the for loop and select the next track and just repeat everything. If you hit back, it will subtract 2 from T, and when it falls through, if T is greater than so it subtracts 2, but then the for loop causes t to increment 1, and the net result is that t goes minus 1. And so the track goes back, and it just simply repeats and calls MFS and starts doing this all again. Otherwise, if you haven't pushed one of these buttons, we check to see whether the buffer's 0 byte is equal to 21. And so that would be that the header of the subchannel request, if it's not 21, it's probably because nothing's playing. And if nothing is playing, well, if it is 21, title end, exactly. If it's 21, it means that the region we've asked to play, it's not playing anymore. And so it will immediately leave here, and it will return to 6500. So it'll immediately return from here, and then it will simply keep playing. And that is literally the whole program. And so now we're at 1 hour 46 of our third episode here, our third video. So all told, it's taken 5 hours and 46 minutes to reverse engineer this program. But I now have, and I hope you have, a deep understanding of how this works, such that we could turn around and we could re-implement this program from scratch and probably do a better job in BASIC. And maybe I will do that as a first step. Maybe I'll do that as a first step. And then later I could implement it as a C64 OS utility, but I have to put a lot of thought into exactly how the utility would work, because when you quit the utility, as we can see from this, if you tell the CD-ROM to only play one song, then when the song is done, if the program is not still running to compute and tell it to run the next song, it's over. It won't automatically move to the next song. So we'd have to think about how to do it in the user interface such that if you quit the utility, the music keeps playing as you want it to. But when you open the utility back up, it would need to read in the table of contents and also know where exactly it is, what song it's currently playing, and so on. There's also a Scuzzy command for pause, for playing and pausing. This program doesn't use it, but basically you can hit the pause, you can send a pause command, and then you can send the play command immediately after, and it will simply resume without having to do any crazy stuff. There was another command that I found in the manual that I thought was pretty cool, which is that for the start, when you send play MFS and you specify the minute, second, it was MSF, sorry. When you send the play MSF command and you specify the start minute, start second, start frame, and the end minute, second frame, if you send the start MSF as FF, that's a special code that means don't modify the pre-existing playhead, which allows you to change the end position while it's already in the middle of playing. So what's cool about that is that in something like a C64 OS utility, maybe while the utility is open and you see the track list and you say, well, start playing from this track, that because it's open, it could start playing from that track, and it could say that the start and end will be the start and end of that track. And if the utility is still open, then it could programmatically progress it to the next track and the next track and the next. But if you leave it playing when you close the utility, it could read the end number from the last track in the list and update the play length so that instead of being from the current track to the end, instead of being just to the end of the current track, you could adjust the end all the way to the end of the album just before you leave the program. So that's an option. Random is the only thing that I don't think is possible if you quit the utility. Because random is not built into the Scuzzy command set. At least I don't think it is. Random is the program controls the randomization, and the program basically looks at the table of contents, randomly picks which track you want to play, and does a play MFS for the start and end of each track. And when that's done, the program has to be running in order to pick a new random track. And then it goes back to the table of contents and does a play FS for the start and end length of that next track. Okay, wait, before I go, there was one other thing I was going to say. Yeah, I remember what it is now. Because this is a basic program, and basic is only ever doing one thing at a time, while the music is playing, it goes into just a loop. It just goes into an infinite loop, just calling the play position command over and over and over and over again, and just updating the time over and over and over and over and over and over. I don't think that is something that's viable. I mean, in C64 OS, excuse me, if you did open a utility and it was above, whatever, the desktop or something, or the file manager, and you clicked a track to play, and it had a total length and a whatever. It had a count of where you were in the song. It doesn't make it's not. There's no way that thing could just go into an infinite loop and just keep polling the CMD hard drive infinitely. I think what you would do is you would use a timer, maybe a 1-second timer, and maybe you don't have to poll it every second. Maybe you could just update the time programmatically, but then maybe you'd have some sort of a keyframe syncing thing, like maybe every 10 seconds you could poll the device to make sure the song's actually still playing, and or maybe to readjust your time just in case the C64 OS timer is imprecise or gets delayed for some reason by the user doing something. every 10th second, it could request the Scuzzy command just to get it back in sync. But ultimately, the timer would mean that, you know, other things are going on, and then only once every second would the timer fire, and that's just enough to update the user interface of the utility while the rest of the program remains active. Anyway, stuff to think about. So thank you very much for watching, and hopefully this has been informative. It's been really fun to do this. See you next time.